Our last topic is chapter 11, which is dealing with heat exchangers. So let's start to define heat exchangers. So heat exchangers are devices in which heat is exchanged between two fluids at different temperature. So we have two fluids at two different temperature. So this is basically the definition of heat exchanger. So in general, heat transfer in heat exchanger involves convection in each fluid and conduction across the wall. So for instance, if you want to just think about, so the simplest design is double pipe heat exchanger. So you can have a hot fluid in one side, a cold fluid on the other side. So the convection happens through the fluid, and across the walls you have conduction. So heat exchangers are very commonly used in industrial practices, especially in chemical engineering. There are various chemical engineering operations that heavily rely on heat exchangers. So we must really understand heat exchangers really well. So this is basically one of the most crucial topics on heat transfer and also in chemical engineering. So what are the applications that rely on heat exchangers? So process industry, oil industry, chemical industry, polymers, plastics, power generation. So biomass and biofuels, bioethanol, biodiesel, food industry, beverages, dairy, sauces, fruit, meat, prepared food. So in food industry, the flow characteristics of the food depends on temperature. So you must make sure you control the temperature well so that you can control the flow behavior. Sometimes you may need preservation processes that requires high temperature. So to kill the bacteria, so you may need to rapidly heat and rapidly cool a food commodity. So as you can imagine, there will be a lot of food applications that rely on heat exchangers. So in the previous case, in the process industry, so most of the chemical reactions are highly sensitive to the reaction rate, highly sensitive to the temperature. So you want to control the reaction rate to optimize the reaction yield. So in electronics industry, so you always use, all of your computers, laptops have some sort of heat exchangers to cool the CPU. So there are also other electronic devices that requires high frequency, so they require high exchangers, high frequency devices, radar system, laser systems, and nowadays also power conversion devices. For instance, power inverters in electrical cars, they also have heat exchangers. So as you can imagine, when you have thousands of batteries, small batteries in an electrical car, they generate a lot of heat, so that heat has to be dissipated, and this is another area where the heat exchangers are being used. So now, after we define define the heat exchangers and talk about the industries that rely on heat exchangers, so now let's talk about heat exchanger types. So broadly speaking, we have three types of heat exchangers: direct type, storage type, and direct contact type. So direct transfer type of heat exchangers is basically the simplest design. So here we have a cold fluid and hot fluid that flows simultaneously across a device, and the device is separated by a wall. So this is one of the simplest designs. So you have double pipes, or two concentric pipes. So one fluid is in one section, another fluid is in the annulus. So, and the heat transfer occurs across the wall, but heat transfer is basically facilitated by convection. The second type of heat exchangers are storage type heat exchangers. So in this case, we have a large surface area, large container, and hot and cold fluid use this surface or this container, same surface. So they basically, but however they operate in a discontinuous fashion. So for instance, if you need to heat up some cold fluid. So let's say you have a waste that is initially hot. You fill the container. This has large surface area. This has high ability to store energy. You put your waste in the container, heat the container up, and then drain the waste, and then you basically fill in the cold fluid that you like to heat, and then this is basically how it operates. So of course you want to make sure that the waste and the fluid that you want to heat up is compatible. If there is any, for instance, impurities or chemical reaction between these two, you cannot use this. So this may be only applicable for certain types of systems. For instance, if you have immiscible, let's say oil, hot oil, and you want to use cold water, so maybe that could be one area. So you may want to think about what are the processes or what are the types of the fluids you can use in this kind of fashion. So the other type of heat exchanger is type C. This is direct contact type heat exchangers. In this case we have direct contact between cold and hot fluid. So in this case we must have two immiscible fluids. Okay, two immiscible fluids. So for instance, so you may be using hot gases, let's say combustion gases, in a large container, and you want to heat up some cold fluid. So you basically drain the fluid down against a hot fluid that is flowing up, and then they will come into contact, and there will be some mixing, and there will be some heat transfer, and this is basically that's the idea behind the direct contact type of heat exchangers. Obviously we require two immiscible fluids, and if you are dealing with two different gases, the gases are always miscible, so you cannot use this process for two different gases. So at least I mean, if you have one gas, the other phase has to be liquid. So other phase can also be solid. For instance, you may have small granules that are falling down against a hot gas. So you can have a solid gas, liquid if the liquids are immiscible, or you may be spraying some liquids against a solid surface, or you may have two different solid streams. So these are all possible combinations in direct contact type of heat exchangers. So now, after we go through all of these, so now let's talk about direct transfer type heat exchangers in detail. This is the type 1 that we talk about. So in many of the heat exchangers, the fluids are separated by heat transfer surface, so that they don't mix, they don't leak, and this is usually a wall, but it can be something else. Such exchangers are referred as direct transfer type or recuperators. So this is an alternative name. So I prefer to use direct transfer type, but this is a name that you may encounter in the industry sometimes. So what are the types, what are the different possible direct transfer type heat exchangers? So you can have a tubular, so it can be a concentric tube, which is the one that I showed you, or shell and tube. You can have plate type, and you can have extended surface type. So let's take a look at the concentric tube heat exchangers. So this is the most simple design. So you have two coaxial tubes. In one tube, hot fluid, in another fluid, in another tube, a cold fluid. So the position may change, so it may, depending on certain criteria, we'll talk about this later on. So you have one fluid that goes in the hot side, another fluid that goes into cold side. And the next type is called shell and tube heat exchangers. So in this case, instead of two concentric tubes, so you have a very large shell. So this is the white area here, this is the shell. And you have many tubes inside this. Okay, shell is the container, and that carries one phase of the fluid, and the tube is the another phase that carries the another phase of the fluid. And again, these you can literally have hundreds of tubes inside, and you want to make sure this is sealed well and it operates well. So let's talk about the nomenclature of the shell and tube heat exchangers. So in general, so we always have a shell. We may have multiple shells, of course. So we count the number of shells. In this case, in this figure on the left, we have only one shell. And then tube is doing 1 and 2 passes. So we count the number of passes by the tube and the number of container shell. So we have one shell, the fluid is doing one shell pass, and then the tubes are doing two tube passes. The fluid in there doing two tube passes. So you may have another type. So you may have a barrier here. So let's say you may have a barrier here. Or it's separating, it's the fluid. So you have one pass and two pass. So we have two shell passes. So ideally you may think this is one shell pass, this is another shell pass, and then you have 1, 2, 3, 4 tube passes. So you count the number of passes on each side, shell side and tube side, and you report that one, and that is the name of the shell and tube heat exchanger. Okay? So if you want to take a look at further details of the shell and tube heat exchangers, so we have some other elements that we may need to consider. So for instance, so we have baffles here, okay? Baffles here. So as you can see, the reason for the existence of the baffles is to direct the flow around the tubes, okay? If there is no baffles, the flow will just continue in a straight fashion. That means the mixing will not be very good. So that means the heat transfer will be less effective. So you introduce baffles outside the shells, it's outside the tubes, inside the shell, so to guide the fluid, okay? So you have a shell inlet, shell outlet, and then you have a tube inlet and tube outlet here, okay? And in industrial practices, there are various different types of the front and rear end head types. So I'm not going to go too much into detail on this, but I want you to be aware of. They have different design. For instance, for the front head, so we may have a bonnet type of front head versus you may have a rectangular design in here. So the idea here in general, you want to, if you are using high pressure fluids, so the curved surfaces are more resistant against high pressure. So if you have corners, they tend to create leaks and problems, failure mechanisms. So in general, if you have a sharp corner, that is where you tend to have failure in high pressure applications. So for instance, you might want to use this kind of geometry to avoid that kind of corner effect. So you can have, shell types. You can have one shell pass, just going one straight. So you can have two shell passes. So you can have a split flow. So you may split the flow, and then you may have double split flow. So each of these provides different mixing geometry, different advantages and disadvantages. So, and you might want to think about what is the scale of an heat exchanger. Heat exchanger can be huge. So if you take a look at this freight here, so this is a huge scale heat exchanger. And you may have literally hundred tubes inside. So if you even try to count them, it will take a few minutes to count them. So basically, depending on the industrial scale of the application, then you may need to use hundreds of heat tubes and very large scale heat exchangers. And the next is basically plate heat exchangers. So this is another type of direct transfer heat exchangers. In this case, instead of tubes, we have plates that basically control the flow, and they basically control the heat transfer. So in general, they have a very small footprint compared to the other one. They have very small footprint, but if you just think about the number of plates here, these are all vertical plates that are stacked here. So it has very large surface area. So one advantage of this kind of heat exchangers is easy to assemble and disassemble. So you can unscrew it from here on the side, and then if you know one of the plate is rusty or corroded, you can just remove it and replace it. Or you can even clean it if there is some dirt that build up there gradually. So one issue with this kind of heat exchangers, you cannot use them in high pressures because it is a semi-open design. So you are basically somehow sealing it from the seams between the plates. It is not very reliable, as opposed to you have a completely rigid system in a tube. You build something that is fully closed, and that can basically that's more resistant against high pressures. So here I'd like to show you more about the flow behavior. So you have basically channels. So you have one stream for cold fluid that goes in, and it follows, let's say, the odd number of plates, goes into 1, goes into 3, 5, and so on and so forth. And then you guide the hot fluid, and that goes in the even number of plates, so 2, 4, so on and so forth. So there is always a contact between hot and cold fluid through this plate. Okay, instead of a pipe wall, you have a flat plate that controls the heat transfer. And as I mentioned, you can easily remove one of these, so it is not difficult to do so. So another type is extended surface heat exchangers. In this case, so idea here again is simple. You are separating two fluids. So for instance, you may be using corrugations and fins. Let's say we have two plates. So plate 1 here, plate 2. They are filled with fins in between, or in corrugations in between. So what is this doing is increasing the surface area. So increasing the effective convective heat transfer coefficient. Okay, so you have one fluid going in this way, another fluid going that way. So you are trying to maximize the contact between them by introducing these corrugations. So another type is you can have a tube, and that has an extended surface. So if everything is flowing against, let's say this, there is a oil here, and let's say there's a hot gas here. So we have cold oil, we want to heat this up. So that could be one possibility. So you can flow the gas around this extended surfaces. So you can also arrange the, so now let's further, we talk about different types of direct contact heat exchangers, direct transfer heat exchangers. So now, so far we talk about direct transfer heat exchangers. Now we'll talk more about their classification. So they can be classified with respect to their flow arrangement. So you can have parallel flow. So that means both fluids are flowing in the same direction. You can have a counterflow. So both fluids are flowing in opposite direction. Or you can have a cross flow. So the flow is orthogonal. So one fluid is, let's say, towards you, and another fluid is normal, so orthogonal to the pipes. So these are the most common flow geometries in heat exchangers. So you can also classify heat exchangers with respect to their surface compactness. So this means how densely the tubes are placed with respect to one another. So if the tubes are very, very close to each other, so this is basically, it becomes compact. So if the separation between the tubes are far, it is less compact. So usually if you are dealing with a gas fluid heat transfer process, so the compact is defined as what is the surface area per unit volume. So if it is greater than 700, it is compact. If it is less than 700, it is non-compact. So if you are dealing with liquid-liquid process, so in this case, the compact means the per unit volume you have, for per unit square meter cube, you have 400 square meters area. And if it is less than that, you have non-compact. So this is just industrial heuristic for naming compact versus non-compact for different heat transfer processes.